We physicists have waited 100 years since 1916 for this photograph.
Hello and welcome back to Universal Narratives. Over the past couple of decades, extensive research has transformed our understanding of black holes, massive celestial objects weighing anywhere from 2 to 4 million times the mass of the Sun. We've transitioned from knowing virtually nothing about these enigmatic entities to gaining increasingly detailed insights. Recently, Michio Kaku made a groundbreaking announcement. We have finally peered into the inner workings of a black hole. This revelation sheds new light on aspects of black holes that the scientific community may have previously overlooked. Join us as we delve deeper into the mysterious and mysteries of black holes and unveil their hidden secrets. But before we explore Michio Kaku's findings, let's address some common misconceptions and gaps in our knowledge about black holes. In 1916, Albert Einstein introduced his theory of general relativity, which included a prediction about the existence of black holes. However, during that era, black holes remained purely theoretical. It wasn't until the half-century had passed in the 1960s that the scientific community obtained evidence supporting the actual existence of black holes. Researchers were studying the Cygnus constellation when they observed an unusually bright blue star emitting X-rays. Upon closer examination, they realized that this star was not stationary. Instead, it was in orbit around a massive, mysterious entity. Even more intriguing was the fact that these X-rays weren't simply moving independently. They were being drawn into the gravitational pull of this enigmatic object. This is what they call the black hole. This discovery held immense significance because it confirmed that black holes were not just products of Albert Einstein's theoretical musings, but real cosmic phenomena. However, it also posed a challenge, as it meant that there was an incomprehensible entity in space that demanded further exploration. Researchers from around the world embarked on studying this black hole, named Cygnus X1, located approximately 6,000 light-years away in the Cygnus constellation. Following the revelation of Cygnus X1, scientists initiated extensive researches for additional black holes. Their investigations led them to suggest that there could be a staggering number of black holes within the Milky Way galaxy, potentially exceeding 100 million. However, due to the immense difficulty in detecting these elusive cosmic entities, we have yet to establish an exact count. Nonetheless, it appears that there are several, indeed million, black holes within our Milky Way, which underscores the significance of studying them. Many individuals hold the belief that black holes are far more intricate than initially perceived. To reach the nothingness at the core of black hole, one must navigate through its first two layers. The initial layer is known as the event horizon, representing the point of no return. Once you cross this boundary, there is no turning back. Things only become more perilous beyond this point. The second layer, the photon sphere, is a region where light revolves around the black hole. Any light that enters this region becomes trapped and cannot escape the gravitational grip of the black hole. Lastly, we arrive at the third layer, which is a singularity. Here, everything that enters the black hole undergoes extreme compression until it reaches a state of infinite density, becoming a singularity. The singularity marks a point in space-time where our known laws of physics break down, rendering the outcomes unpredictable. Adding to the complexity is the fact that each black hole under study exhibits unique behavior. While they generally adhere to the three-layer concept, their specific characteristics can vary significantly. If this were any other scientific inquiry, we could rely on telescopes and detailed observations to study the matter. In the past year, several groups of physicists made separate groundbreaking announcements. They revealed that string theory could offer a comprehensive solution to the challenges posed by quantum black holes, albeit in a reduced two-dimensional context rather than full 10 dimensions typically associated with string theory. Many physicists maintain the belief that it's merely a matter of time before someone successfully addresses the problem. Nevertheless, it's premature to start planning intergalactic voyages or time-traveling expeditions, especially concerning black holes. Michio Kaku has elaborated on how one can discern the genuine answer amidst these myriad theories. He emphasized that the issue of having an infinite number of solutions is not exclusive to string theory. In fact, many profound theories possess an infinite array of solutions. For instance, Newton's laws can predict the motion of various objects from rocks to rocket ships, but you must specify precisely what they're seeking and what you're seeking to explain before you can forecast their behavior. Similarly, in the realm of string theory, you must inform the theory about the specific phenomenon it is addressing. However, unlike other theories, string theory's initial conditions are intimately tied to the very moment of the Big Bang itself. Currently, these initial conditions remain a mystery as we lack precise knowledge of the conditions at the instant of the Big Bang. There are a couple of approaches to tackle this challenge. One avenue involves empirically determining the initial conditions at the moment of the Big Bang and then employing string theory to elucidate the subsequent evolution of the universe. Notably, there already exist string theory solutions that delineate the universe's evolution from Big Bang based on reasonable estimations of its initial state, marking a significant accomplishment. Alternatively, a more ambitious approach entails demanding that string theory autonomously selects its own initial conditions. This path, however, presents a greater degree of complexity and challenge. We've already made significant strides in narrowing down our understanding of the Big Bang. However, Michio Kaku introduces a unique perspective. Perhaps the Big Bang wasn't as massive or noisy as commonly envisioned. The crucial question arises: what transpired before the Big Bang? This is where string theory becomes relevant. According to this theory, our universe could have originated from the collision of two separate universes have emerged from another universe akin to a newborn emerging from its mother. This connection between universes is termed a wormhole, resembling a tube linking two bubbles. It's conceivable that we may have already unearthed evidence of this cosmic umbilical cord connecting our universe to another. In essence, we could potentially be inhabiting the interior of a black hole without realizing it. Consider this intriguing possibility: we may be residing inside a black hole all along, oblivious to this cosmic reality. To contemplate this concept, ponder the limitations of our existence within four dimensions. Our conception and perception is confined to this four-dimensional realm, preventing us from glimpsing anything beyond it. As a consequence, it becomes plausible to entertain the notion that our entire existence unfolds within a black hole. Furthermore, the black holes we diligently investigate might not merely be gravitational sinks, but rather gateways or wormholes to alternative dimensions. Could this theory hold any kernel of truth? We invite you to share your thoughts and insights in the comments section below. If you found this video enlightening, please express your appreciation by giving it a thumbs up. Stay tuned for our next installment, where we'll delve further into the mysteries of the cosmos.